Okay, so let us start the session for today. So today is the last day of the workshop. So we have two things to cover today: unsupervised machine learning and also the object detection using Cascade classifiers. So we will try to do both. So we are taking 3 hours today as you instructed. So 10 to 1 p.m. we are going to go up to, right? So first we will discuss about unsupervised learning, and they will move to the clustering, and we will discuss about the k-means clustering, and the k-means clustering will be then used to, then we will use the the k-means clustering algorithm for this kind of implementation. Uh, we will use the k-means clustering in order to uh, segment tumors, as you can see in a minute, right? So we are going to see how we can detect tumors from a scanned image. So this will be the practical for today, right? And we will discuss on how to do this in the practical today, right? But before going on to that, we need to discuss about what actually clustering is. Then thereafter, we will move on to this practical application, right? Okay, so unsupervised learning. Now, the second section of machine learning. So we know the supervised learning, unsupervised learning, and reinforcement learning. And unsupervised learning, we discuss about the classification algorithms as well as regression algorithms in the past 4 days, right? So today we are going to move on to the unsupervised learning and discuss about a topic called clustering, right? So what do you mean by unsupervised learning? When it comes to unsupervised learning, the main important thing is that in unsupervised learning, we don't have labels, right? That means when we are dealing with unlabeled data, then we have to use unsupervised learning. Now, for example, the first day we took example like, okay, the temperature, humidity, and whether it's going to rain today or not, right? So that kind of a situation, we have the labels. So the required or the expected labels are there, but unsupervised learning, we don't have labels, right? So what do you mean by we don't have labels? Is that we are going to deal with unlabeled data, right? So then you may be wondering what is the purpose or what are the applications of unlabeled data and what we can do with unlabeled data. That means there are no any targets or labels, right? So in that case, what we can do is using only the features, right? Unsupervised learning always most of the algorithms tries to predict labels, right? Predict labels. Or we say in unsupervised learning, we have unlabeled data. That means we have only the features. So according to the features, we are going to identify some hidden structure or hidden relationship between these data points using the features, right? We don't have targets, we don't have labels. So what we'll do is we'll identify a hidden relationship uh, in a given feature set, right? And probably we are going to label them, right? Unlabeled data, we are going to identify the relationship between the unlabeled data and we are going to label them. So that's what clustering simply means. Unsupervised learning simply is most of the unsupervised learning algorithms when it comes to clustering as well, right? So in order to, unsupervised learning, we have lots of examples like clustering, dimensional reduction, right? So we have lots of methods available. Lots of uh, sections available in unsupervised learning. So one section is clustering, right? So what do you mean by clustering is, like, you can see a very good example here. So if you have a mix of data, you don't know the labels, only the features. For example, the color available and the size available and the shape available, weight available. Now those are some features, right? Size, then the color, right? And the weight, right? Uh, those kind of things, right? So let's say, then what happens if we apply clustering? Clustering is simply according to the feature. So that means considering the feature. So we can say, like, taking similarity in between the features and identifying the relationship between features, we are going to group those data, the provided the mix of the data into several groups, or we say clusters there, right? Clusters. So once you have unlabeled data, clustering simply like take some features, for example, here the size, weight, color, and everything, and using the similarity between those features, we are going to like cluster each data point into groups, right? Understood. So that's what simply clustering means, right? So clustering, there are lots of other methods of doing the clustering, right? Like hierarchical clustering, k-means clustering, principal component analysis, mean shift clustering. So lots of clustering methods available. But what we are going to actually discuss today is about k-means clustering, right? So we'll discuss about k-means clustering today. And the second type, that's about clustering. We have another type in unsupervised learning called association, right? So what do you mean by association? Like by considering the similarity between some features, it's going to like uh, suggest some uh, I mean, yeah, so, suggesting recommendations, right? Or giving recommendations. For example, now sometimes you will see YouTube and Facebook most of the times, right? So you are suggested ads and you are suggested some kind of videos, right? And some kind of in Facebook, some kind of groups, right? So in that case, sometimes you not be the target. That means you are. That prediction or that suggestion is not based on you sometimes, right? Now what I'm trying to say, in YouTube you may see some suggested videos, and Facebook's you may see some ads, and in Facebook also you will see some group suggestions and everything, the pages, right? So you are asked to like pages, right? So and friend suggestions, right? Exactly, indeed, friend suggestions, right? So these things are usually done using this unsupervised machine learning, like association methods. Now it's like this. Now let's take someone like you, quite similar to you, like the age, the region where you live, right? And the profession, or the field you are following, the degree you are following, right? And your gender. Likewise, considering those features, now if someone similar to you from that features, like the age, gender, and the the region, the university that you are, or the university or the institute that you are currently studying in, likewise, and the subject and the fields that you are following in, right? So if someone like you, if that person is in a group, let's say, okay, machine learning group, deep learning group, right? Or something like whatever the region to some group dedicated to your region or your school. So according to him, now the association methods thinks, okay, that you are a similar one to this the guy that I explained, right? Since you have similarities in the features, right? So then what will happen, you will be given suggestions like according to his favors, right? So that the association algorithms thinks that, okay, since you have similar features, you are similar to the other person, so you may be uh, you may like what he likes, right? So similar kind of a thing, association methods, right? So but we are not going to go with the association algorithms most of the times, but we will only go to the clustering topic today, and we will cover the k-means clustering today, right? Okay, so clustering is about, as I mentioned, once the data set is given, the purpose is to group the data set based on the similarity of the features of the given data set. Now, we don't have labels here, right? We don't have labels. That means you have this kind of, okay, the feature one, right? The feature one and the feature two, right? So when the feature one and feature two are there, so you are going to label them, and you are going to uh, group them into classes or cluster them into classes. So this is like zero class for one and two, right? That means clustering is simply about labeling unlabeled data based on the features, right? Based on the hidden uh, relationship between the features. So that's what you call as clustering, right? So here we have very important points, right? Two important points, right? So this explains, okay, cluster refers to a small group of objects. Clustering, the verb, is grouping those objects into clusters. And third point, in order to learn clustering, it's important to understand scenarios that lead to cluster different objects. Now, these points are quite important here, right? When it comes to clustering, and if you perform clustering, there are two methods that you need like always keep in mind. When you do clustering, when you perform clustering, that means clustering about grouping or clustering unlabeled data set. When you are going to do that, that's a very important thing, that the points in the same group should be similar as possible, right? That means that, okay, so if you are going to cluster some data points into a one group, all the points in that group should be similar as possible. That means they should be quite close to each other. That actually represents that they are the same. That means they are in a they have the similar characteristics. They have similar features. That's what it means by they are quite close to each other, right? That means, okay, when you are going to perform clustering, no matter what's the method, this will be the base idea, that when you perform clustering, in clustering we labeled unlabeled data set. When you are going to do that, that should be done in such a way, like when you perform clustering, you need to cluster the data points into clusters by considering that the same, I mean, the points that you are going to cluster into the same group should have very similar features, right? That means those dot points should be very quite close to each other. I mean, if you consider 2D, I mean, two features, right? So then you can identify if the points are quite closer to each other. That means they are having similar characteristics. They are having similar features, right? And the other point is points in the different group should be dissimilar as much as possible. That means if you consider a 2D scenario, right? Between two clusters, the data point should be quite, I mean, as far as possible, right? As far as possible from the each cluster. That means that actually represents that the data points in two different classes have like, they are very dissimilar to each other. They are having not even, I mean, they don't have similar characteristics, since they are quite, I mean, they are far away from uh, the data points in each cluster, right? Got it? So, and don't think that the clustering is always about circles, right? No, clusters are not always circles in circular planes, right? Circular objects. Sometimes you can have this kind of distributions as well, we will see, right? Okay. So, clustering is used in lots of applications, right? So, in marketing, right? So, now there can be like always when a new product is, I mean, new product is introduced, right? So the potential customers, right, or the already existing customers, we can uh, cluster them, right? We can cluster them. Okay, those who have like machine learning, those who are like deep learning, those who are like marketing, those who are like project management, those who are like likewise. Understood? So we can segment the already existing customers in some kind of a platform, right? And in biology, right? So this is a very important thing now. Uh, why this COVID-19 said to be a virus, right? Can you understand why it's not a bacteria or any other kind of thing, right? So this hints like the COVID-19 or the coronavirus is clusters is cluster, categorized under this corona, right? Corona set of virus. So in corona, you have some other viruses as well, right? So SARS, MERS, those kind of viruses. So when it comes to even dengue, right? So how it is classified under corona or the viruses section, since the corona, right, or the COVID-19 has similarities that has to virus, right? The similarities that they are in virus, right? So that's why it's classified as a virus. So no matter when a new kind of disease comes, right? So if it is a virus or bacteria disease, what happens? Always it will be classified under like a virus or bacteria. Now that's something like depending on the characteristics or depending on the features, it will be categorized under virus or whatever the other thing, right? Understood now? Movies, libraries, songs, right? So thrilling and comedy, right? And love stories, right? So horror, right? So those kind of how the categorization is done. Now, I mean, that's something depending on some features, right? Depending on some features, some attributes, some characteristics of that film or the book, right? So if the content is having this kind of things, okay, it's a horror movie, right? Or if it is having this kind of a thing, so it's an adventure or thriller. Got it? Likewise, now the everything is done based on features, right? Understood? So now earthquake studies, right? So I mean to predict the areas dangerous or safe, right? So we can use like similar features and do these things, right? Got it? So clustering is, I mean, right? Clustering is a very important algorithm. I mean, in our day-to-day lives as well, right? So in healthcare also we use, right? So you can identify, okay, right? So now you know something like, so in the coronavirus as well, right? So we have different clusters, right? From the, like, we, when a new patient is identified, that patient will be uh, grouped into a cluster, like, okay, this cluster from this area, this age, this region, so he will be in this cluster likewise, right? So clustering is used in lots of applications, right? Okay, so we will now talk about k-means clustering. So anyway, clustering is about grouping these objects. So let me show you a practical application and let me explain how clustering works, right? So we have the rain data set. I have given it in your uh, file, right? So this rain data set has two features, temperature and humidity. So it is in the rain dataset.csv. So when you run this one, you will see this kind of a data set, right? So now you can't say, okay, so these are the rainy days and these are not no rain days. No, you can't say it like this is only having, I mean, don't think that there is a label in this data set. No, there are no any labels. We have only the temperature and humidity. So these are some days where the temperature and the humidity are recorded, right? Where the temperature and humidity are recorded. That's all. No labels. We don't have any idea about whether the data set, I mean, whether a particular day is a rainy day or not. We don't have that such a idea here, right? So what we have is simply we have a data set, and this data set simply uh, when you plot that data set, you are going to see something like this. Okay, this is some temperatures and humidities in some, I mean, 13 days. That's all, right? So let's assume that we want to cluster these data set into like two clusters, right? Don't think that, okay, when you are going to cluster this data set into two clusters, that don't think that it will be like rainy data, I mean, rain days and no rain days, right? So how many, I mean, okay. So, okay, one cluster, right? So we are going to manually do it at the first time. The second cluster, right? So is this the only method of clustering, right? Right. So let me show you another method. Now we have lots of possibilities, right? So here, one cluster, another cluster, right? Or else what we can do, I mean, I wanted to show you that there are lots of way to perform clustering here, right? Not only one way, right? Okay. So the data points are divided into two clusters in this case, right? Understood? So that you can see that we can perform clustering. So what is clustering? When you have no labels, when you have only features, grouping those data points into different clusters. So that's the idea of clustering, right? Okay, so let me show you how the k nearest neighbor actually uh, do this, right? So what we are going to do now, we have some unlabeled data, right? So we have, to be exact, we have 13 data points, right? We have 13 data points here. I mean, 13 temperature and humidity pairs, right, in this data set. So what we'll do here, we apply now, before explaining you how k-means clustering works, let me apply it and show you, right? So let me apply it and show you the output, then we are going to move on to the theory part, right? So now in k-means clustering, the specialty that we can provide the number of clusters we need, right? The number of clusters that we are looking for in this data set. Number of clusters that we are looking for in this data set. So that's the n cluster equal to. Now, this is the k nearest neighbor. This is the special property when it comes to k-means clustering. K-means clustering. In k-means clustering, you can provide the number of data points or number of clusters that you are looking for. But if you comes to mean shift clustering, another clustering method, mean shift clustering. In mean shift clustering, we are not going to provide the number of clusters. Mean shift clustering actually divide the data set, or it clusters the data set accordingly into some clusters, right? So the number of clusters are not given. The number of clusters is decided by the mean shift clustering when we apply the mean shift clustering. But k-means clustering, the specialty is that we can provide the number of clusters that we are looking for, that we are expecting here, right? So what we'll do in now data is this 13 points, right? So data simply two columns and 13 rows, right? 2 columns and 13 rows. 2 columns and 13 rows, right? Temperature and humidity. So unsupervised learning, now model.fit. Up to now, what we have used, train data, test data, train data, train target. Train data, train target. Hope you can remember. But in unsupervised learning, as I mentioned, we don't have any target, or we don't have any labels. So therefore, what we'll do, we only apply the data. That means we only apply the features here, right? So we use model.fit, and unsupervised learning, we only apply features, so we apply the data here, right? Then what happens, the k-means clustering algorithm, what it does is it cluster these data points into clusters, right? And then the cluster number, so we asked to cluster them to 2 clusters. So then there will be like cluster 0 and cluster 1. Since we asked for 2 clusters, cluster 0 and cluster 1, right? 0 and 1. So thereafter what happens, we can see those labels, the labels in the sense clusters. I mean cluster, the cluster, that cluster number that each point assigned into, right? Then we can see the cluster number that the each point is assigned into, right? So what we'll do, that we get something called labels, model.label. So this contains the cluster number of each data point that we applied into the data set. So can someone tell me how many labels will be there? Huh? How many labels? I mean, what's the length of these labels? How many labels you are going to get here? 2 clusters, 0 and 1. I'm asking how many labels will be there altogether? Yes, we are getting answers. Good. Yes, 13. Very good, right? 13. Since we have 13 points, each and every point will be clusters. So we have 13 clusters. So it says, okay, this point is in cluster 0. This point is in cluster 0. This point is in cluster 1. Likewise, it gives us the label for each and every data point. So that's how what happens here, right? So now if I go through the whole data set and if I check the label, Whether if the label is equal to 0, I use the blue color. If the label is equals to 1, I use the red color, right? So then you will see something like this. Right? Now these are the two clusters that the k-means clustering has identified. The cluster number 1 and the cluster number 2. Okay, so which one is the rain class and which one is the no rain class or the no rain cluster? Any idea? No rain red. The x-axis is rain and the y-axis is the humidity. No, you can't say that this is the rain class and this is the no rain class. No, right? No, we can't say it like that. I mean, it can be, right? So what you think might be okay, right? So what you think might be accurate, but actually we can't say always like that. Okay, this is the rain class and this is the no rain class, since the k-mean clustering algorithm, it simply gives you some data points and it has identified some relationship, I mean some similarity in between those data points, right? So that's why it is clustered into the red and other points are clustered into the blue. So what the k-means clustering algorithm has identified, it has identified some similarity in between these two. That's why it clusters into these kind of things. Now it doesn't know, okay, this is the rain or no rain. That's what some idea that we have, right? But this is some mathematical relationship. That's what you have to always identify. This is some mathematical relationship that it has identified. So now, if you want 3 classes in the same data set, right, you can still get it, right? See? Now, what this means then? Huh? So what this means then? No, that we can't say, okay, this is the rain or this is the no rain classes, since this is clustered based on some mathematical relationship between these points, some similarity between these points, but we can't exactly say, okay, this is this class and this is this class. We can't say, right? So if you ask any number of clusters, it will provide us whatever the cluster required. Got it? Right? Okay, so the other most important thing is when a cluster is originated or when a cluster is defined, a group is defined, then each group has a cluster center, right? A cluster center. So we can get the cluster centers. Now we have only 2 clusters. I think we will have 3 clusters. So let me run this again. The 2 cluster thing, right? Okay. So then you will get to know that when you are getting cluster centers, there will be cluster centers which equals to the number of clusters we expect. We asked for, right? Now the other important thing, now k means clustering. The k simply refers to this number, right? K simply refers to this number, right? K means this number that we are going to provide. K means clustering. And so the number of clusters that you are going to get will be equal to the k, right? So then now you can see, okay, this is the cluster center 1 and this is the cluster center 2. So why we have like 2 coordinates in the cluster center? Each cluster center we have 2 coordinates. What's the idea behind that? Yes, the x and y, that means the features. So we have 2 features, right? That's what it represents. So we have, if you have 4 features, there will be 4 coordinates. If you have 10 features, there will be 10 coordinates in each cluster center, right? So the coordinates that you are going to get in each cluster center will be equal to the number of features, right? And the number of cluster centers depend on what? What? The number of cluster centers depend on what? Number of cluster centers that we are going to get depend on what? Depend on what? Number of cluster centers, simply it is equal to the k, right? So if you are looking for 3 classes, there will be 3 centers. If you are looking for 10 classes, there will be 10 centers. Each cluster has a center, and the number of coordinates in a cluster center will be equal to the number of features simply, right? So if you plot those points using x and y, if you use x and y and if you plot them, this is what we are going to see. Okay, this is the cluster center of the blue cluster and this is the cluster center of the red cluster, right? Then the other most important thing, right? This is the beauty of unsupervised learning. Now, once you apply the unlabeled data set into a machine learning algorithm, I mean clustering algorithm, it cluster those data points into required number of clusters. Simply that's what happens. So when you simply ask to cluster the data set into clusters, right? What happens is like the unlabeled data set will be labeled, right? For example, now this was the data set and we applied it to the k-means and this is what we got. So now these are labeled, right? These are labels, labeled into 2 labels, right? Thereafter, what will happen? That we can now use it as a what? We can now use it as a supervised learning problem. That means we can use model.predict. For example, now if you apply an unknown data point to this, it can give predictions. For example, okay, 32. Let me use a color like this. Okay, 32 somewhere here and 70 somewhere here. Okay, somewhere here. Okay, now my question. After labeling an unlabeled data set, that means after model.fit in a k-means clustering algorithm, then we can use it for future predictions, right? Okay, so then I'm going to apply an unknown data set. So can someone quickly tell me what this prediction would be? It's a red point or a blue point? 3270. Quickly. Blue, blue, blue. Okay, depends on what? Why you say like that? Huh? Based on the nearest neighbor? Yeah, but not, right? The nearest, yeah. So this will be red. This will be red. Why? It's not looking for the nearest neighbor. It looks for the nearest cluster center. Right? It looks for the nearest cluster center, not the nearest data point. So this will be a red one, right? So that's how it gives a prediction. So it gives the prediction based on the nearest cluster center, not the nearest neighbor, right? Got it? So a bit different compared to k-means clustering. Right? So anyway, my point is that we can use this for future predictions after doing this thing, right? Got it. Right. So now, yeah, I hope you understood everything about k-means clustering, right? Now we have to quickly see how k-means clustering works, right? So I have like three possible, yeah, okay. Now, this is how the k-means clustering works. Simply let me explain you, right? Now, if you need like two clusters, right? If you need two clusters, you have unlabeled data set here. So the first, the first thing, okay, you are going to see how many clusters you need. Then what happens? Randomly, two data points will be selected, right? Two data points will be selected randomly. This is totally random. Two data set will be selected and they will be assigned into the clusters. Now, number of clusters that you are looking for. So since we have two clusters, so I'm going to assign them into two clusters like this. Right? Randomly selected data points, totally randomly selected. So what then happens is simply that the cluster center, now the cluster is represented by one point. So the cluster center lies in the point, right? The cluster center lies in the point since it's like represented by one point, right? So thereafter what happens, right? So all the other points will be clustered into one out of these two, right? So based on the distance, okay. So I think this point is nearest to this one, right? This cluster. So what happens then? When a new data point added to the cluster center will be shared by the both points, right? So it's going to get the midpoint of these 2 points, right? Midpoints of these 2 points. How we are going to like get the midpoint? YC and MC, right? Sorry, YC and XC. XC and YC, let's say. Center points, XC and YC. Right? So this is how the point is calculated, the midpoint. So the mean shift, I'm sorry, K means. So the center moves, right? Center moves, right? So then what happens? Each and every point, as I mentioned, okay. So this point, what do you think? Is it to the red one or the blue one? I mean, the red one or the green one, this point? I think it is to the green one, isn't it? No, it's the red one. Eh? I'm asking about this point. What do you think? Is it nearest to the green or the red? Now it always now measure the distance to the cluster center. Right. So since you all say green, I will make it a green. I thought of like red, but anyway. And so now the cluster center moves to a common point. Then nothing to say, right? Nothing to say. You know that all the points this side definitely will be right. Got it? So then the point somewhere like it moves to somewhere here. I think somewhere here, the center. And I think these 2 points will be somewhere here. And then the cluster point, the center moves to somewhere here. Okay, so this is a one example. One iteration, I mean, one possibility actually, right? But anyway, now this is not the only possibility, right? So can you remember the first step? We selected the first points first 2 points randomly. So we have like n number of methods doing that, right? Okay, any idea? Okay, out of these 13 points, selecting 2 points randomly, how many possibilities are there? Out of 13 points, selecting 2 points randomly, how many possibilities are there? Yes, 13C2, right? Yeah, I wanted to, I want to like, you can get it, right? So statistics and probably like we have some equations to get this, but I can't exactly remember what the equation, but the, yeah, permutation. And the thing is now, it is not infinite. It's not infinite, right? 13C2, right? Okay, so we have some finite number of times doing it, but anyway, uh, like, okay, let me select another 2 points, like, okay, this is red and this is green. So now you know this will be, sorry, this will be definitely green, and point will be here, and this will be a green, right? And the point shifts here. And this point definitely would be a red, and this point also be a red, right? And also this would be a red, and I think this also would be a red. So what about these points? Probably this one is a green. So then it moves somewhere like here, I think, right? Then if you consider this point, probably it's in green, and this also in green. So the point should be not exactly like, it lies somewhere here. So this point definitely would be a red one. Right, so roughly this is what happens, right? Okay, so what do you think? Huh? What do you think about the first one and the second possibility? What would be the best one? I mean, by looking at, can you provide me like what's the first one or the second one? By looking at, you can see that one is good here, right? Out of these two. Yeah, the second one is good, right? The second one. So you can see like why there's a good separation. Now, what I wanted to say is like, not that here. You will see it now. If I draw a circle bounding these points, okay, something like this. But here, what happens in this one? Right. So this is like if you mark the cluster boundaries, this would be something like the cluster boundaries, right? Got it? Right. Okay, so the idea here that you can see, right? Can you remember the 2 points, the 2 principal points I mentioned? The data points in the same cluster should be close as possible. In other words, we can say should be similar as possible, right? In the, if you compare two data points in two clusters, different clusters, the data point should be dissimilar as possible, right? But you can see now, if I mark these 2 points, right? So can you see these 2 points if you take, right? So these are, I mean, they are in green cluster, but they shouldn't be in the green cluster. Can you see, right? Since they are not even close to the center, right? So they are not close to the center. So they are from like deviated, right? So due to that reason, can you see the circle, right? The radius or the diameter of the circle gets large, since like these 2 points are not relevant to this data set, but due to that random selection, these points are selected. So that makes this circle a large circle, right? So the circle, that the bounding circle, if the data set or if each cluster has very similar data points, the circle should be, the diameter of the circle should be minimized, right? That marks that, okay, so if you have a very small circle, right, with a less radius, that marks, okay, that says simply the data points in this cluster are closer to each other. That's why the radius or the diameter of the circle gets smaller, right? Gets smaller, right? So the idea here that the second one said to be good, right? So not by looking at, but there is a theory to say that, right? So we declare something like this, right? So we declare something like this, and this is called the variance. Not exactly matching is my one, but this is called the variance. The variance of each. Now this is the variance of the cluster one, and this is the variance of the cluster two. Right? Variance of the cluster one and variance of the cluster two, right? So the total variance, there's a parameter called total variance, right? TV, total variance. And the total variance would be equals to V1 plus V2, right? V1 plus V2. So any idea how to select the best? Now, the k-means clustering runs through each and every random first point selection, right? So it's going to select points randomly several times, and out of them, how to select the best clustering instant is by selecting the minimum total variance out of this. So this is an iterative algorithm. What I mean by iterative, so this will done again and again repeatedly, right? So two random points are selected, right? And two random points are selected. Thereafter, what happens is like we are going to measure the total variance and go to the next two random point selection. Likewise, we select random points again and again randomly. And each time we measure the total variance. So can you the best clustering method or the best clustering iteration or the best clustering instance is selected when it has the minimum total variance, the minimum total variance. Understood? So keep that thing in mind. This is the iterative algorithm which runs again and again, but it selects the best one. Like similar to support technology, can you remember that we draw the hyperplanes again and again, and the best hyperplane will be selected by the minimum margin, the hyperplane which has the minimum margin. Similarly here, the minimum total variance, right? So actually what this says, right? So now this satisfies the two requirements. The data points in the same cluster are closer to each other, right? As much as possible. If you take the total minimum total variance, and the data points in different clusters are dissimilar as possible, right? Got it? Understood? So that's what happens in clustering. To be exact, the k-means cluster, right? Understood? So that's how k-means clustering works. Any questions from your side? Anything to be clarified? Okay, great. So thank you very much. Now, I think you have understand the content. Okay, so let us go to the practical implementation from this. Variance is nothing but the diameter. No, not exactly. Diameter in the sense, yeah, it can be considered as the diameter. So, like the variance simply would be the, okay. So if you have let's say the farthest away data points, right? So the distance between the farthest away data points. That's what you call the variance of the cluster. Now we have other data points, but the variance will be the right, right, the distance, the maximum distance, like between two data points, right? Maximum distance. So that marks the diameter of the circle that bounds this class, the cluster. All right. So now, very interesting application that we have to discuss today. All right. So I think that you can see that there's a folder called test images. Right? A folder called test images in your working location. Right? Which has these scanned brain tumor images, which has like the cross sections of the brain where it has cross section and cross section of images which has brain tumors in it, right? So what we'll do now, we in the right. So the first thing now, what the purpose is to like segment the pixels in this image into different clusters, and we are going to define a cluster that actually represents the brain tumor. Understand? So now this data set has several pixels, right? Several pixels. So to be exact, the size is 512 into 512. So we have like around several hundred thousands, right? Several hundred thousand pixels here. So what we'll do here, we apply the image into a clustering algorithm, to be exact, k-means clustering. And we are going to like cluster these pixels into different classes, right? We cluster these pixels into different classes, and we are going to identify a cluster which represents these brain tumor cells, brain tumor pixels. Understood, right? Again, so you know that we have how many pixels here? Uh, I think 512, something around 200,000. Yes, we have 200,000, 262,144 pixels in this case, right? So what we'll do here simply, each and every pixel out of this will be clustered, right? Will be clustered into a, we are going to cluster it to a different cluster, right? So what happens is, thereafter, out of those clusters, we are going to select the cluster that represents the brain tumor cells or brain tumor pixels, right? So let's see how we are going to do it. So I'm going to read the sample image available in this test images folder 0239 JPG, and I load it as a gray image, right? 0 simply says that it to load it as a gray image, and we print the shape, so it's 512, 512, and we show the image in matplotlib. So this is what we are going to see simply, right? Thereafter, what we do now, I think you asked this question in earlier examples as well, that Can't we apply 2D into a machine learning algorithm? No, not in most of the algorithms. So what you have to do is you have to flatten it, right? So what we'll do it, we flatten it to a column vector, not a row vector. We flatten it to a column vector. That means height into width. That means this number and 1. So we flatten the image. Now this is not flattened as a row vector. This is flattened as a column vector. I will let you know why, right? Right. Okay. So then we have something like this. Okay, we have 262,144 pixels. Now these are pixel values, and one says like, okay, one single column, right? So when you I have printed the first 1,000 of this, right? So I think all the pixels are black, right? Why all the pixels are black? Since I think the first 1,000 would be somewhere here, right? So let me print the first, let me print the, like, okay, 50,000 into 50,000 and, I mean, right, so you can see now, okay, these are the pixels from 50,000 into 51,000, right? So you can see some values, right? Now, what I want to show you here, that this image is flattened into a flattened, yeah, a 1D image, right? A column vector, all the pixels. No, this is the shape that you are going to obtain, right? So this 2D image, 512 into 512, now flatten into this kind of a thing. So it has a flatten now. You can remember this when we did the early examples in the character recognition as well as in the face recognition system. We flatten the image first. So the same thing is done here. Then what we'll do, now I will do it like 2, starting 2, right? So I apply the flattened version of the image, right? We apply the flattened version of the image into the k-means clustering, and we ask for two, what? We ask for two clusters, right? We ask for 2 clusters. So then we can get the labels of each and every cluster. So can you identify how many labels will be there? How many labels will be there? The length of this label array, any idea? Again, others, what do you think? How many labels will be there? Yes, exactly. Yeah, others, yeah, number of pixels, exactly 262,000, whatever the value. So that amount of labels will be there. If you can't, if you, now each pixel, right? Each pixel will be simply, right, assigned into a label, right? Can you see? Now each pixel is assigned into a cluster out of 2 clusters, out of 2 clusters. Then now we can't visualize the 1D thing, right? So what I'll do is I reshape the image into the earlier shape, right? So that means what? I'm going to reshape it back for the purpose of visualizing it, right? You can't visualize a 1D thing, right? So uh, uh, see, so we reshape it back to 512, 512, and this is what we are going to see. Right? Now, actually, this shows now how many possibilities are there in the labels? How many possibilities? How many possible values are there in the labels? How many possible values are there in the labels? Yes? 2, very good, right? So it's 2. Either cluster 0, either cluster 1. We have 260,144 values, but the possibilities are 2, right? So what happens here? It shows, okay, when you, I mean, let me show you. Um, Shall we see some values here? Right. See, so now this is from 5. These are the pixels from 50,000 to 51,000. So you can see like either one, either zero, right? Either one, either zero, right? So when you, this is what you are going to plot, right? The 2D version of this one, right? The 2D version of the labels we are going to plot. So what happens here, that it represents 0 and 1. So two colors. So 0 for the label 0, it uses the this kind of a dark purple color, and for the label 1, it uses this yellow color, right? So now, has it identified the tumor correctly? Can you see a tumor here? Yes. Can you see a tumor here? No, right? So therefore what we do, right? So tumors are not identified. So any suggestion? What we need to change here? So simply 2 means the background and the foreground. So 2, now we are going to separate the image into 2. Cluster image into 2, so the background and the foreground simply, right? So we increase the cluster, see? We will check it. Okay. Still not detected, right? Still not detected. Now the background and the brain and the outline of the skull, right? So 3 clusters are simply, okay, 0 is the inside of the brain, and 1 is the outside, the background, and 2 is simply the skull, the outline of the skull, right? So it's not already done yet. So increase it. Can you see now how the clustering simply works? Okay. Now, can you see some green parts are detected, but not the tumor? Tumor not detected one yet. So we'll use 5 and see. Okay, perfect. Detected. But shall we now apply some other value and see whether it's what do you think? 6, is it good, or 5 is working well? I'm not sure. Let us run again. What do you think? Is it 5 or 6? So this is 5. I think 5 is good, yes. 5 is good, yes. Okay, now here, okay, if you use 5, can you identify the cluster number which gives us the tumor cells? Roughly gives us the tumor cells. Yes. Now can you identify the cluster number which gives us the brain tumors? Brain tumor pixels. We will run it again and hope that we get a different color. Okay, now can you identify roughly? I'm not perfect, but can you identify the cluster which gives the brain tumor cells? Quickly. Yes, which one? The number? Yeah. So can you identify the cluster number of the yellow part? Yes, the yellow pixels. It's 4. Very good. It's 4, right? So now keep in your mind that, okay, the brain tumors are represented by 4 now, right? So now what we are going to do, so we have trained algorithm and we have saved it here. Now we are going to test it, right? See how we are going to do it. In the second call, testing the model, testing the model. So what we'll do is we get the algorithm, the brain tumor segmentation algorithm, and we run it, and we open the image, another image from the test images folder, right? And what we do is we simply get it here, and we reshape it, right? We reshape it, and we get the flattened version, right? Right. So we get the flattened version. Then what we'll do, we apply that, we take another image, not the same image, right? So what we'll do then, we apply the flattened version to the already trained algorithm. And after getting the labels, we make it 2D and we show it here. Okay, so you can see in this image also the brain tumor is detected in yellow, right? The brain tumor is detected in yellow, right? Okay, so then I'll do something like this. Now what I need to do from here is that I need to get the brain tumor pixels extracted and remove all the other pixels, right? I mean, we need only the brain tumor cells, right? We need only the brain tumor cells. So what we are going to do is we extract the brain tumors and remove all the other unwanted clusters, right? So in order to do that, I'll use this kind of a method. Yeah, this one. So now I will explain how this image is taken. Now here you can see the brain tumor is extracted and all the other things are removed, right? So that's what happened. Happened in this image, right? But let me explain you how that's done. Okay. So you can see now this is example not related to the brain tumor segmentation, but I will show you now what happens here. We have array. Let's say we have array. Now don't get confused that I'm not explaining something related to brain tumor segmentation code. I'm explaining something else. This will be helpful for our this purpose, extracting the brain tumor cells and removing all the things, right? Extracting the brain tumor cells as white, and all the other pixels we are going to make it black, right? So here now you can see we have an array here, a sample array, right, which has these numbers. Then I'm going to do something like this: array 2 equals array 1 equal 5, right? So what it simply does is it checks where in the array 1 where the elements are equals to 5. This is the testing the model, testing the model, testing the model 5, right? Okay, so we are checking whether this one equals to 5. So this is the resultant image, right? This is the resultant array that you are going to get, right? So if you print that, you will see it's like false, false, true, false, false, true. What this means? It's going to check that whether it's going to go through each and every element of the array. It's going to go through each and every element of the array and checks whether the element is each and every element is equals to 5. If it is not equals to 5, it returns false and it assigns false. When it equals to 5, it assigns true. And if it is false again, I mean it is not equal, then false. And if it is true, right? So this simply goes through each and every element and check whether the element is equals to 5. If that's the case, what happens? If that's the case, it's going to, if it is equal, it returns, I mean, it assigns true, but if it is not false, it assigns false, right? Understood? So this is like 1 and 0, right? True is 1, false is 0. So you are going to get a binary array, 0 and 1, right? So remember that the number of elements in the array 1 are equal to the number of elements in the array 2, right? Got it? So we do the same thing. Now we have defined a tumor label here. Yeah, tumor label. So our tumor label is 4, right? So our tumor is now represented by 4. So we make the tumor label a variable called tumor label 4 here, right? Then what I'll do, I'll come here and I'll check in this 2D array all the pixels that equal to 4, and I assign it to the mask. So can you identify here all the pixels, which all the pixel values not corresponds to the cluster 4, since we are looking for number 4, right? So all the pixels that not equals to number 4 will be false. That means they will become 0. All the pixels that has 1, that has 4, all the pixels that has 4 will become true. That means white, right? Got it? Right. So we simply make a binary image. We make all the pixels correspond to the class 4, the cluster 4, 1, and all the other pixels we make them 0. So we are getting a binary image which represents all the other pixels which correspond to all the other classes other than 4. We make them black, and the cluster 4, the pixel correspond to cluster 4 will be white. That means 1. Got it? So we have a binary array here, 2D binary array, right? Got it? Right. So then what you are going to do, right? Then what you are going to do now, yeah. So now you know that this is the image that we want. The mask is the image, but unfortunately, the OpenCV not recognize a binary array as an image, right? The OpenCV does not identify a binary array as an image, so we have to convert it to the form, right? So what we'll do here is we we multiply all the values in the mask by 255, right? What happens? So this one, the possibilities are 0 and 1, right? That means 0 for all the other pixels, 1 for the label, I mean the cluster 1, right? So we multiply each value by 255. So what happens? This will convert the range into 0 to 255, right? This converts the range into 0 to 255. Right? We convert the image into 0 to 255. Right? So 0 and 1 are there. So we convert it to 0 to 255. Now, can you see? Multiply by 255 converts it to a 8-bit number like 0 to 255. Why? When 0 is multiplied by 255, it's 0. But 1 multiplied by 255, it's 255. So all the other middle values will be the same, right? So we convert it to the unsigned int 8-bit form, right? Unsigned int 8-bit form. Since the unsigned int 8-bit is the form that the OpenCV images are using, right? So OpenCV images are, the data type of the OpenCV images are numpy unsigned int 8-bit. So we convert this binary image which has 0 and 1. Now you have to remember that when you check this, all the images, all the pixels which is not corresponds to the cluster 4 becomes 0, and all the pixels correspond to cluster 4 become 1. So this is a binary array with 0 and 1, right? So this is a binary array with 0 and 1. Got it? So then what we'll do, simply we'll then uh, uh, convert it to an image that the OpenCV supports, since we are going to convert it to a range between 0 to 255. And the data type numpy unsigned int 8 is the data type used in OpenCV images, right? So now don't worry about this kernel operation. I will explain it later to you. Right? Uh, so the same thing, but now this is a OpenCV supported image. This is not. This mask is a not OpenCV supported image. It is just a binary array. But this is the image that we got from the uh, this is what we got from the got as a OpenCV supported image. Thereafter, what we'll do, right? So we find the contours of these contours in this image, right? Contours in this image. So this is the image that we have at the, I mean, the this is the latest image that we got. So what we do, we apply that image into a function called find contours, right? Find contours in OpenCV, right? Find contours in OpenCV. So we pass this tumor extracted image, this image, into a function called find contours, and this function actually takes several parameters: the retrieval method and the approximation method. Retrieval method and the approximation method, don't worry about them. These are the default values that we need to pass, right? I'm not going to go into details of this, but I will provide you a tutorial where you can learn about this in detail. See OpenCV. Right, so you can go through this one, and this is a very helpful thing about when you want to uh, learn about contours. So you can go through this link, right? And my point is, now don't worry about these two parameters. These are some default values for the retrieval method and the approximation method. But anyway, once the image is given to this find contours function available in OpenCV, it detects contours. So what do you mean by contours, right? Right? The contours here has a different meaning, yeah, same meaning, but what happens here is that it's going to find the closed areas, right? The closed areas in this image, right? Closed areas in this image. So let me show you this, what I'm explaining on this closed areas, what I mean by closed areas, right? So what happens is, one image is given for the find contours function, it finds us the contours. That means the closed areas in this image. So we print the length of the contours. That means we check how many contours are there, and using this function, we can draw the contours available in this given image. So what it simply does is, it draws all the contours. So -1 simply represents that it draws all the contours available, right? And 0, 2, 5, 5, 0, this is the color of the contour that, I mean, the color of the outline that you are going to draw, and this is the line thickness, right? So let me show you like that. This, can you see? Now these are the closed areas available in this image, right? The closed areas available in this image. Let me remove this one and show you this one. Closed areas, right? So can you see, now we have 740 closed areas in this image, right? 740 closed areas in this image, right? So we draw them all. But if you put 0 here, what happens? Sorry. See, can you see? So it just draw the first contour. 0 is the one, right? So the first contour in this image, right? The first contour of this image out of 740, out of 740. So shall we print the, right? So shall we print the 730? So this will be the last one. It since it's going from 0 to 740, 714, 713 actually. Sorry, let me run it. So this is the contour number 713, right? The last contour. So likewise, it detects all the contours in this one. Right? So all the closed areas. So -1 simply draws all the contours. Right? -1 simply draws all the contours available here. See all the contours. Now you can see that we no need of don't need of having all the contours drawn here, right? So what we are interested is something about the contour that gives us the what, which gives us the brain tumor, right? Not all the contours are important in this case, right? So we need to have a method of tracking only the contour, right? So what we can do is simply we can now this loop, you can see it goes through each and every contour available in the this image for contour for CNT in contour. So this runs 740 times, right? And what we can do in for each contour, we can measure the area. So let me print the area and show you. Right, so you can see now these are the areas of each and every contour. Some of these things are like negligible contours, right? Got it? Okay, now don't worry here, right? So I think this one you can yeah, when you run this saves in your working location, right? So there's a question where this file is located. When you run this will saved in your location, working location, right? Okay, so I mean, you know up to this point, right? So you know up to this point from where in the sense, now I discussed in the first week, right? First day as well. Now when you save it, wherever your code is located, this code is located in that location, this will be saved, this SAV file, right? So this is the train model of the k-means algorithm, right? The train model of the k-means algorithm. So wherever your code located, that location, this file will be created as this. Now you can see. Now this is my code training the k-means algorithm. So this is the file, right? Yeah. So what we do actually, I will explain it again since you told that this is a bit getting difficult. So this image you can identify. So we extracted the cluster 4, the all the pixels corresponds to cluster 4, and we got it. And what we have done here, simply we have make all the other pixels black, and the pixels corresponds to the cluster 4, we have made them white, right? From that, what we are going to do, we apply that this image into a function called find contours. Don't worry about these parameters. I provided a link to read about these parameters, but these parameters are default parameters, just default parameters. And what we are going to get is the contours. So what do you mean by contours? The contours in this image, the closed areas, right? The closed area. So this kind of white closed areas, right? the white closed areas in this one. So when you draw those things, right, so -1, so -1 draws all the closed areas. So this is what you can see then. Sorry, not this one. Let me run this again, this one. Sorry, let me run it from the beginning. These are the closed areas, right? So now you can see we don't need, now what we are going to do is, right, so the final thing will be something like this, that we need to detect the tumor part, only the tumor part. We need to detect the tumor part. So out of these contours, I'm going to neglect all the other contours and get the contour that represents the tumor, right? So that's what I want to do here. I want to get the contour area separated, right? So what we do is we apply the image, I mean this binary image, the black and white image, into the find contours function. So the find contours function returns us the contours. So when you draw it, right, so the -1 is simply, actually it asks you to draw all the contours. Now here, when you print the length of contours, right, the length of contours, so this simply says you how many contours are detected in this image. So it says there are 714 contours are detected. So -1, now in the image we draw the contours, -1 represent, we ask like draw all the contours, right? And this is the color that we use, a yellow color, and this is the line thickness, right? So -1 asks to draw all the 740 contours detected, all the contours detected, right? For example, if you provide 0, this will only plot the first contour, right? For example, if you run this now, see, only the first contour is drawn now, right? So if you like provide 100, so the 100th contour is now being will be shown here. Where can you see? Here, a very tiny little contour. So this is the 100th contour, right? So likewise, what I wanted to show you here is that it has 740 contours, but we no need of having all contours, right? We need only the contour that represents the brain tumor segment, right? So what we'll do, we will go through each and every contour for CNT contours, and we get the area of each and every contour and print the area. So we that I'm having idea to remove all the other unnecessary contours by measuring the area. So this is what you are going to get from area. So we have lots of areas coming, right? These are the areas of each and every contour out of 740 contours, right? So some of them have 5,000 something, some of having like 60,000 area, right? So likewise, we have lots of areas coming here. So let me draw something like this. I'm going to do something like this. I'm going to check whether if the area is greater than 1,000, right? I'm going to check whether if the area is greater than 1,000. And if that's the case, I'm going to draw the contour. I'm going to draw the contour of that segment, and I'm getting a bounding rectangle. I will explain what I mean by a bounding rectangle, and I draw that bounding rectangle. So if you run this one, you will see what happens. Not this one, sorry. Let me run it again. So the bounding rectangle. So what do you mean by the bounding rectangle here? Now I have drawn all the contours greater than 1000. Now, can you see that small dot kind of things are now removed, right? So what this bounding rectangle simply says, when you pass the contour into the function called bounding rectangle, it gives us this values. Like if we take this rectangle, right, x, y, w, and h. So it provides us the bounding rectangle xywh, right? So what we do here is we get the xywh and we draw a rectangle around that using the green color, BGR, green color, and with line thickness of 2, right? Now, this is how the brain tumors are detected, but now you can see the outline is not necessary, I mean, not brain tumors. We have detected this one, yeah, this is the brain tumor, but the other things are not brain tumors, but it's all waste detected, right? So what we did was we removed the unnecessary small brain tumors, right? Small brain tumors, and we select, I mean, small tiny little contours, and we got only the tube, I mean the contours which has greater area than 1000. So then we were able to get rid of the other things. So let me show you now. Uh, right? So we have like remove all the other contours, but this unwanted thing is detected. Why? So the reason is that you can see some, right? Some tiny little things are detected outside, right? Got it? So what we can do here in order to get rid of these things, here we are using something called where here we use morphological operations. I will explain what a morphological operation is, right? I'll explain what I simply do here, right, in a minute. But let me run this again and show you. Now you can see the only the brain tumor is detected perfectly, right? So you can see if you compare this image, right, this image and this image, you can see that the unwanted white color areas, not which not represents the brain tumor, is now neglected, and they are removed now, right? So if you do this now, you will only get the rectangle here, right? So how to get this, the unwanted pixel, white pixels removed, and almost it, not all, uh, from this kind of image, when this kind of image is given, how to like remove the unwanted white color pixels, right? So that's done using this one. This is called the erosion in image processing, right? Erosion. So shall we have a quick look on what erosion simply means, right? I think we probably have something.
Chapter 9. Morphological erosion of this image by our structuring element. Remove.
Right. Okay. Now I'll explain it using this one, right? So that right? So this is what the erosion simply does, right? So it's going to take a kernel. Now this red color 9 rectangle, sorry, square set of values is called a kernel, right? This red color rectangle array is called a kernel, right? So this kernel will go through the image like this. See, so it goes through the image like this, the image like this. Now assume that there are black pixels and white pixels, right? There are black pixels and white pixels, right? So what the erosion does, if you carefully look at this again, right? So this is the input image and this is the output image and this is the kernel. So this is called the neighborhood operation. What it simply does is it goes through the image, right? It goes through the image, right? It goes through the whole image, and at the each instance, right? So here you can see, okay, this point. Now, when the kernel is at this position in the input image, right? When the kernel is at this position in the output image, the value, the middle value of the middle value that corresponds to the kernel in the output image, right, will be assigned into a black or white, right? Will be assigned into black or white, right? So what happens? It assigns black to the middle pixel in the output image compared to this kernel, right? Right. So it simply assign black. Sorry, let me show it like this. Okay, let's have another look and I will explain. So can you see where it goes, like the middle pixel will be always assigned a value in the output image, right? So it always assign black, can you see? But it assign white, can you see? Now it assign white, right? So it assign white when all the 9 pixels here, all the 9 pixels here detect white pixels, right? When all the white, I mean, the kernel detected, when the kernel detects white pixels for each 9 elements in the kernel, then the middle pixel in the output, the corresponding middle pixel in the output image becomes white, right? So here, the next one will also white. The next one will also white. But what happens to the other one? See, now only one pixel is not white, right? One pixel is not detected at white, so therefore that middle pixel becomes black here, right? So now again black, now white, right? So since all the 9 pixels detects white, therefore the middle pixel becomes in the output image the middle pixel. What I mean by the middle pixel, the corresponding pixel to this point, right? So here, this one becomes white, right? Then what happens? Again, that also becomes white. Why? All the white pixels are detected here, right? So likewise, this will go through the each and every image, right? Now white. Now what happens next? Shift by 1, what happens next? If you shift by 1, what happens? Is it a black pixel or a white pixel? See, it becomes white. Since not all the kernels are getting white, right? Likewise, this goes through each and every, it iterates through the image, and does this. So when you can, I mean, see it, you can see the image is eroded, right? The image is eroded, right? So the same thing happens in our application as well, right? The same thing happens in our application as well. Now here we pass 5 by 5 kernel, so you can change it. I mean, the example there was like 3 by 3, but here we pass 5 by 5. So what happens here? Simply it goes through the kernel. I mean, the kernel goes through the image, and it erodes this. I mean, what happens? So then these small segments will be eroded, removed, right? So that's why, sorry, that's why, right? So we are getting something like this from this. Small unwanted small segments are neglected by doing the erosion, right? So here what we are doing, cvd.erode function, we apply the tumor extracted as the input image, and we apply a 5 by 5 kernel in this time, and we iterate once. That means we iterate through the whole image at once, right? And this erosion simply removes the small areas, right? So now what happens is, you can see the tumor is extracted like this, right? So then I have included some other things as well. So I draw a small rectangle here. Let me show you. This is the rectangle drawn from this line, right? A filled rectangle. I think we didn't do it, right? So here we use a filled rectangle. So if the line thickness becomes -1, that will be a filled rectangle. So we draw a filled rectangle, top of the rectangle, the bounding rectangle, right? And thereafter what we do, we simply uh, get this thing, the tumor, like we put a text, like as we did in the Donald Trump, Barack Obama, and everything. So this is what we are going to see now, right? Understood? Got it? So uh, let me share this with you. The only new thing that we have applied here is the erosion, right? So sorry, right? So the morphological operations, you can search about these morphological operations more. Actually, we have two main things called erosion and dilation, right? Erosion and dilation. So this is, for example, if you have an original image like this, right? So it will be eroded when the erosion is applied, and it will be dilated in the sense like the inverse of the erosion, right? So you can search about this morphological operation. So we actually did erosion in our morphological operations, right? Got it, right? So in the next code, what we do is we the training the whole fold, testing the whole fold. The next code, I think it is with you, right? The testing the whole folder thing, right? So here one last thing that now earlier what happened, now I mean, it detects some unwanted contours like this, right? So since there are white pixels like this, right? So when we apply erosion, what happens? Those things are removed, right? Then we perfectly detects the only the tumor, right? So the erosion uh, is important than that point, right? So in the next code, what we are going to do is we simply go through the we simply go through the whole image and apply each and every image in the uh, folder, right? So this is the testing the whole folder code. Uh, so what happens is that we load the brain tumor one, right? And the tumor label is 4 in our case, right? So then what happens? We have declared the image names. That means test images. We get all the image names into this array, right? We get all the test image names into this array. The images, the names of the images available in the test images folder. Thereafter, we go through each and every image. We have done this in that what the face recognition thing as well. I think you can remember. We iterate through the uh, fold and we uh, read the all images and we perform the pre-processing. I hope you can remember. So similar thing is done. Similar kind of a thing is done. So we go through each and every image and we load. I mean, we create the image path by joining it with the test image, and we read the image. And after reading it, we reshape the image before applying it to the algorithm, and we apply it to the algorithm, right? And we get the 2D version of the labels, and we create the mask, and the mask will be converted into an image, a OpenCV type image, and we apply the erosion, right? And we find the contours as we did earlier, and we filter the unwanted contours by going through each and every contour and measuring the area. So we draw the contours, right, greater than 0, right? So now you will see when you are going to do this, you will see it like this, right? So the tumors are detected like this, not all the times tumors, but I mean, what happens uh, if you don't check this kind of a condition? I mean, okay, if one, that means now there's no any condition check, all the images will be drawn. Now this if condition is always true, right? So we don't uh, uh, make any decision here. We draw all the contours. See now what happens. See, for example, if you remove this put text and this rectangle, then you will identify what happens actually. See, now how many tumors are detected, right? Can you see how many contours are detected, right? So it's always you have to measure the area, right? You have to always measure the area, and you have to print the area and have an idea about, like, right? I think you can remember, right? Have an idea about the area, right? Have an idea about the area. That means you have to print the area and you have to get the idea, okay, where actually these tumors are located. Now if you print the area, now you can see 2 0.5 10 84. I think this is the tumor, right? So you can see 2000 something, 2000. Now there is nothing larger than 2000, right? So I think that's the tumor. So you can measure the area, so others will be removed, right? So what I'm going to do now, I don't measure the, I don't draw all the contours, but I will draw the contours greater than 2000, let's say. Now 1000, let's say. Now you can see only the required contours will be taken. This neglected area contours will be removed. Got it? So then you can have this rectangle and also the tumor one as well. Now it's detected like this, right? So now the thing is, don't think, okay, that I mean, sometimes you are not going to understand this at once, right? But you have all the codes and you will get the video today as well, right? So what you have to do is please go through these things and try to cover them again, right? And you have to always play with these codes, right? You have to change these codes. Now don't think that I'm going to, okay, give you the whole knowledge and everything about machine learning, image processing, everything. No, right? So these sessions, these workshops are simply like covering the fundamentals and everything, like you want to get it started, right? So if you are a beginner, now you have a good opportunity, you know about everything. I mean, everything in the sense, you know, supervised, unsupervised algorithms, and you know how these things works. And so this is a good start for you all. Now you can search in the internet and you can find new things and start working on your own projects, right? And meantime, if you go through the same course again and try to implement some things, and I mean, try to implement something and change these codes and see what are the results, right? So that's how you learn it. Otherwise, okay, this workshop is over, now we are like fine and everything is done, we are expert in machine learning. No, you are not experts in machine learning, even like, you know, very simple things, right? So very fundamental things, but this is the start. You can change these codes, you can play with these codes and see what are the changes of the output. That's why that's actually what I see as the most effective way of learning, right? So I always, when I'm going to get a code, I will go through like the top to bottom of the code and I try to understand each and every line, right? So that's the method of learning these things. That's, I mean, this programming and coding, machine learning theory you can get, right? Without any doubt you can get the machine learning theory. But in order to right, in order to uh, in order to implement it, right, you need the practical knowledge, the coding knowledge, but coding skill. Coding is not a knowledge, it's a skill, right? So you are not going to get it by reading a book. You have to implement it, you have to implement codes, you have to change codes and see what are the differences. So it's a skill. So in order to gain the skill, you have to always work with these codes. Otherwise try to understand by reading it, no, that won't help you, right? You have to always go through the codes and change these things, and you have to run these codes and play with the codes and see like how it happens. And that's the only method of getting this skill, right? Okay, so I hope you can understand what we did in the brain tumor segmentation. So any questions from this section quickly, if you have any doubt? Okay, so seems not, right? So we will quickly now go through the next topic that we are targeting to cover today, right? uh, the object detection thing. Right. So now here I wanted to show you, before starting that, I wanted to show you that this is the working location for today's the object detection thing. So you need to have these files with you, right? You need to have these files with you. Um, the samples folder, which has something like this, and also the cascades folder, which contains some cascade classifiers, right? Cascade classifiers, and also this samples folder, as well as the vehicle detection and counting folder, which has a video of bikes and another uh, file, right? So the IPython notebook, right? So I think you have this file with you. I have already uploaded it to your Google Drive, right? So assuming these files are with you, this face, video, flower, everything, and vehicle detection and counting, right? Everything. Now we will quickly move on to our implementation, right? So before going on to object detection, now you know what image is. So we have discussed about this in previous implementations as well. So images are 2D arrays, right? So computer sees a image as set of numbers, right? Set of numbers in a two-dimensional array. So we know that we have three types of main image types. We have three main types of images: color, gray, and binary. So when it comes to color, so if you take a single pixel, you know that the pixel can be named by see the row number and the column number, right? So pixel has an index, that means from the column number and the row number. So if you look at the pixel, that pixel simply contains three components if it's a color image like BGR, right? So every element is a 8-bit number. And similarly, in gray images, you have 0 to 255. That means gray images, 0 is black and 255 is white, and anything in between is a gray value. And binary images, you have 0 1, that means black or white simply, right? And thereafter, we have like these are the the color image, and this is the grayscale image, and this is the binary image, right? So uh, in OpenCV, simply you can read images by providing the path of that image, right? Providing the path of that image, right? So we load the image into this one in this tutorial, right? So we load the flower image, an image called flower, and we print the image 100. So let me show you the output. So this is the image that is shown because this imshow command and wait key, you know, it waits infinite time when it provides 0, and after pressing any key, this window will be destroyed. But what this means, print 100 by 100. So that means it's simply, okay, this value, right? So we can then conclude that this is a RGB, or the color image, right? So it has BGR components. So it's obvious. Can you see? Huh? BGR. So R is maximum and bit of blue is there. So it's a red color, right? Exactly, it should be, since you can see this 100 point pixel value should be a red color value, since it's something where this, inside this flower, right? In this flower. So that definitely should be a red color one, BGR. Got it? Right? And so we can perform arithmetic operations in these images as well. You can see now what we have done. Okay, 100 to 150, 100 to 200. We have made those set of pixels white. See, 100 to 150 in y direction, in the y direction. And so first we go through rows, right? So that means y direction, and then we go through columns x direction, right? So 100 to 150, 100 to 200, we have make it kind of a white pixels, right? So I just wanted to show you that we can perform arithmetic operations as well as in images as well. Compared to other arrays, right? Okay, now we will having that basic knowledge about image, we will go to something called Haarcascade classifiers. And as I mentioned yesterday as well, day before yesterday, Haarcascade classifier is a bit old technology, but still in use. It's still in use for very useful applications, right? So it's quite easy to use a Haarcascade classifier. So implemented by Viola Jones, Paul Viola and Michael Jones in their research paper in 2001. So this is where the first idea came into play. And it's a machine learning based approach, right? And a cascade function is trained from a positive and negative images, right? So the other thing is a cascade classifier one single cascade classifier can detect only one object. That means we have cascade classifiers for faces. So that cascade classifier can detect only faces, right? When we have a cascade classifier to detect bike, that can only detect bikes. Likewise, each cascade classifier can detect a single object. So cascade classifiers are trained. One cascade classifier fire can be trained for detecting only one object. But when it comes to present, we have neural networks and we have convolutional neural networks, and those neural networks, most of the neural networks, like using convolutional neural networks, they have implemented something called object detection APIs. So these object detection APIs at once, a single object detection API, that means single neural network can detect multiple objects, right? For example, some neural networks can detect 100 different objects when an image is given. When the image is given, it can detect 100 objects using one neural network, right? So that's the power of the convolutional neural networks. Now that's something about uh, convolutional neural networks. See, for example, now here, mouse, cell phone, bottle, laptop, and everything, right? See, so a single neural network can detect multiple objects when it comes to object detection APIs, right? Okay, so but this is a bit old technology. A single cascade classifier is used to detect a particular object, right? So you can read about cascade classifiers in OpenCV documentation, but I'll simply explain why a Haarcascade classifier simply does, right? So Haarcascade classifiers detect, looks for features, right? So like these kind of fundamental features, edges, right? So what I mean by edges, so white line. So if you have, so when you have, what do you mean by edge? So if you like, say, let's you have a face, right? So this is edge, right? This is edge. Since the background or the white, let's say white, and then you have the face. So this is edge, right? So this is edge, right? So that's what you call edges. And what do you mean by this? This is a line, right? I mean, if you take your nose, that actually looks like a line, right? Right, line. Since you are going to find again white pixels after that, right? So if you carefully see, these kind of features are there in our face as well, right? See, now eyes, what, like top white and middle black, or the other way around, right? And you compare like the nose and eyes, right? So nose part is bit white and the eyes are black, right? So it's a line feature. And if we consider this horizontal like this, it's a edge feature. It's a edge, right? Horizontal edge. So this is a line, right? So likewise, what happens? The Haarcascade classifier, as I mentioned in kernels, right? What happens is that the Haarcascade classifier goes through the whole image that you are going to provide here, right? The whole image that you are going to provide, and it checks, right? It checks whether these features are present in that image, right? So it goes through the each, the image, and it's going to check whether these line features, these kind of uh, edge features, these simple features are presented in the given image, right? If it has a line feature, that means there are eyes. If it has this edge feature, that means, right? So if all the features, like almost all the features that should be there in a face is there, then it's going to conclude that this is a face image, right? So it's going to look through the whole image and check these kind of, if there is these kind of features are there. Okay, if you can find, okay, line feature, edge feature, and again line feature, like the features that correspond to this face, if those features are there, so it's going to conclude that the face is detected, there's a face, right? So simply it goes and checks these features in our images, right? So that's what simply happens, right? So that's what how a cascade classifier simply works. One image is given, it looks for these kind of features are available, and if the features needed to be there for a feature is there, right? If the features needed to be there for a face is there, what happens is going to conclude that there is a face, right? So what happens in the Haarcascade classifier, simply we can load the Haarcascade classifier. So I have provided you lots of Haarcascade classifiers. You can check it. It has faces, upper body, full body, smile, right? Number plates, vehicles, cars, bikes, right? We have lots of cascade classifiers. You can provide the, you can check the folder that I have provided you. All the cascade classifiers are included. You can even download it from the internet as well. But what we'll do, we get a classifier, the face classifier here. Now we are going to perform face detection. We have already done this in our implementation as well. So then in the face classifier, what we can do, uh, we have to always convert the image into a gray color before applying it to the cascade classifier, since it's a requirement. Almost all the cascade classifiers are trained on gray images. Since this is a technology invented in like uh, 20 years back. So in that time, there were no that kind of performances, well performing computers in order to process color images. So they did it all using gray images. So therefore, these are trained for gray images only. And also, is it going to be a matter to, is it going to be the color feature? Is it going to be a matter to face detection? What do you think? Is it going to be a matter, the color for the face detection? No, right? Otherwise, how we can detect African, how we can detect American, how we can detect Chinese, how we can detect Russian? So they have different skin tones, right? Skin tones. So they have different skin tones. So the color is not going to be a matter. Some of their hair like brown, right? Blonde, and some of their like sometimes red, sometimes black, sometimes brown, right? So different colors, right? So different eyes, different, right? So all the things are different, but no matter the color, no matter the hair color, no matter the skin tone, no matter anything, but for each human, right, these features will be there, right? Eyes, nose, these kind of features will be there. So what matters is these features, not the color, right? Therefore, it's okay to convert it color, but what happens when you are going to detect fruits? Is a color going to be a matter? Fruits, let's say apple, orange, right? Guava, right? So is a color going to be a matter in that case? Yes, definitely, right? Otherwise, how we are going to identify the difference between like apple and orange without the color? Quite the same. I mean, the shape bit different, right? So the color is an important matter. I mean, the color becomes important in lots of cases, but most of the times, color is not going to be a feature important. But some applications, the color might be an important feature, right? Got it? Uh, so therefore, now, right? So what you can do then? This gray image can be applied, right? This gray image can be applied to the detect the face classifier. There's a method called detect multiscale, and we apply the gray image, and there are some parameters to be passed, right? There are some parameters to be passed. I'm not sure whether those parameters are mentioned here. Let me check. These two are here. No, 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 no. Um, I think I have included somewhere. No, isn't it? Yeah. Yeah, the scale factor. Uh, I will provide this is to this as well, right? So the scale factor and the mean neighbors. So these are the two parameters that I have provided here, the scale factor and the mean neighbors. So these parameters are tunable parameters. Tunable parameters in the sense that you can change these values and get the optimal detection, right? So the as I mentioned, the scale factor and the mean neighbors, mean number of neighbors. So you can read about those things from the file that I have provided to you, right? So these are like two parameters you can change then and optimize the phase detection. Now, can you remember when we use that cascade classifier for the face recognition algorithm? So the tie detected, some background is detected, right? So we can minimize those faulty detections, fault positives, right? We can minimize those false positives by simply adjusting those parameters, right? Yes. So object detection is a supervised machine learning algorithm. Actually, as I mentioned, when this is done, it trains a machine learning algorithm to two classes, for two classes, positive and negative. So image is provided and says the image is not there or image is there, right? So if you want to detect faces, so the algorithm is trained like positive images, that means contain images contain faces, and negative images not contain faces. That's how it's trained. I'm not going to talk about the training, but anyway, it's a two class classification problem. It's going to provide us positive images like images with faces and images without faces. That's what it simply does, right? So then what happens when you like detect a object? Now these parameters you can fine tune and get some optimal value, optimal face detection. So you can, these values, like we can't have like unique values, we have to always change this, and according to your uh, properties you have to get the color condition, I mean the light condition, right? The quality of the image. So depending on those parameters also you have to change these values, right? So it's application dependent, right? It depends on the light condition, it depends on your quality of your images likewise. Okay. So face classifier, we apply the detect multi-phase. So we apply the gray image and we take the faces into this object, right? So these faces, as I can remember, as I mentioned you in the last time, so it is something like this, a two-dimensional array, right? Which has rows, number of rows equal to the faces detected in the frame, and the columns simply will be equals to the uh, x, y, w, h parameters of the image. So if you have two faces, the faces look something like this, right? So x, y, and wh of each face, x, y, and wh of each face, right? Got it? So what happens is that we can go through each and every phases. So what happens here? Yes, yes, exactly. Uh, yeah. So that's what happens, Shita. Yeah. So now what we are going to do, we go through each and every phase and we get xyw of w, xywh of each phase, and we draw a rectangle and we show the image, and we destroy the windows after pressing a key, right? So this simply iterates through each and every phase. So if you have 10 phases, this loop will run 10 times and get xyw of each phase and draw it, the rectangle, right? So simply this is how the phase detection is done. So then what we do is we can do it for a image as well, right? So I think did we use some image in this case? No, right? Not. Okay. So here, this is how we are going to do it for image, right? This is how we are going to do it for an image. Now, if you want to do it for your webcam, you can provide 0 here. So 0 simply refers to a webcam, right? So the video source becomes your webcam then, right? So then in an infinite loop, what we'll do is we read each and every frame, right? We read one frame from the image, one frame from the source, sorry. We read one frame from the source and we take it here, right? So yeah, before explaining it like that, let me show you like simply how what this simply does. Um, right. So let me show you how the open source, I mean, video is readed from OpenCV, right? So first you have to provide the source, the video source. So if you put 0 here, that means you are going to load your default webcam. So if you put 0 here, it means that you are using your webcam as the source. Now, the other thing is that don't now in my computer, I don't have a webcam, so therefore I use a video available in the working directory, right? So this is my desktop. So but you can use 0 and get the image. I mean the camera, your default webcam, right? So what happens here? We define the source, the video source. Then from that source we read one frame, right? We read one frame from that source, right? Then this read function, the source.read function, simply returns you two things. One thing called read and the other thing called the image. So this is the real frame. The real frame, one frame read from your video source. And the read simply is a binary value. What we are interested on this image, so this contains the frame, one frame read from the video source, right? This read is simply 0 or 1. So this red becomes 1 when the video source is available, that the frames are available in the video source, right? So if the video source provides you frames, the source becomes, the red becomes 1. If the source is not available, or if the source is not providing you uh, frames, the red becomes 0, right? Got it? So sometimes, let's say, okay, I will show you. Let me print this red. So if you are like, let's say if your camera is not working into a technical issue, right? So likewise, then it will return 0. So let me show you that. So this, can you see from the video, it has read one frame, only one frame. It reads one frame here, right? And we show it and we wait infinite times, and we once the key is pressed, we destroy it. But here you can see it, the ret is true. That means the video source is available. But let me, like, by accident, let me change the name here. So that kind of a video file is not there. That means the source is not available. The source is not available. So therefore, can you see it? It prints false. That means that source is not available, right? And it also shows an error, since you can't show an empty image, right? So you can't show an unavailable image. That's why this error comes. But what I want to show you is this false. So if the source is not available, this will red becomes false. And the other most important thing, this gives false when the frames are finished in this video source. If all the frames are read and no more frames to be read, then the uh, red becomes false, right? Got it? So now this is simply how you can read I mean, a single frame from your image. I mean, single image from your video or the video source. So do you have any suggestion on how to, like, continuously do this and load it as a video, continuously play it? Any idea? So this is how we are going to do it once. How we are going to do it continuously and read the video. Now this only reads one frame from the image. Yes, any idea from your side quickly? Yes, iterate it inside a loop, right? So what we'll do, the source reading is on, I mean, declaring the source is 1. Then what we'll do, uh, no, like, we can't apply infinite wait, right? So therefore I apply like 10 millisecond delay. Ah, sorry. Um, I made a small mistake here. So the destroy all the windows should be done at the end. Otherwise, uh, image is shown, then the image will be, I mean, the video is destroyed. Right now it works, right? Right. But there's a small issue here. What's the issue is that you can see at the end you are getting an error here. So the finally you are getting false. Why? Huh? At the end of the video you are getting false here. What's the reason? What's the reason? Yes, the video is over. That means no frames are left. So that means it's not available. So that becomes false, right? So this gives you an error and the code terminates. So in order to get rid of this error, what we can do, we can keep a track of the ret, and if the ret equals false, what we can do, without allowing the imshow to give an error, we break the loop, right? Without allowing the loop, I mean the imshow to give the error, this error, right? We break the loop once the ret is false. So now no any errors are shown, but when the video frames are not available, it simply right. So it simply, you can see, right? So what it does is it simply like provide false and return. No any error is given, right? Got it. Now, but we have another issue here. Uh, that once this image is loaded, we can't stop it. We can't stop it. Once you close it, it opens again, right? It opens again. Why? Now, if we close this image window, since it iterates through a loop, the same window will be opened again, right? So we can't close this. Once you close it, again, since it's going through the loop, next frame will be opened, right? Therefore, what we can do is when we press a key, we can get that key here, right? We can get that key here, right? Did I discuss about this thing, the key and the ASCII value and how to destroy a window? Did I? Yeah, we did it, right? I think we did it. Did we? Yes or no? Or can't you remember? The others? No idea. Anyway, so we can, I mean, this wait key simply waits until the key is pressed. You know that, right? So we can check this key and value of this key. If we press 27, we can break the loop. So now this 27, no need to exactly be 27, but this is the ASCII value, right? The ASCII value. So 27 now you can you can have your own value, but I'm using 27 since 27 is the escape. Sorry, here, yeah, escape. You can see 27 is escape. So what happens once the video is running? If I press escape, all the things are terminated. Right? Everything will be terminated. So you can stop the video whenever you want by using the escape key. But you can change the key you want. But I use the escape key. So when I press escape, this loop breaks and it destroys all the windows at the middle of the code. Right? See? Right? So once the escape key is pressed, this will destroy it. So that's how you are going to deal with the video. But anyway, now what happens here? You can see it gets XYWH, right? And what we can do is instead of this, we can apply it. See? Right? So now faces are detected. So we get XYWH and we draw the rectangle with this XYWH and we put some face, I mean, a text as face as well here. Right? So now the next thing is how to detect eyes. So we have another cascade classifier in the same folder called eye, where we can use it for detecting eyes, right? So I load the same thing. I mean, I load the eye classifier as well, right? And what I'll do, I'll go through the face first, right? And draw the face. And then I'm going to extract the face. What I mean by extracting the face, I get the face extracted. So let me show you what I'm trying to do here. This is what I mean by the face image. So you can see the face is extracted. Now we did this in the early example as well, right? I mean the face recognition. So you can see the face is extracted, only the face, right? So you can see the face is extracted, only the face is now cropped. Now what happens? You know that eyes will be there definitely inside the face, right? Eyes will be there definitely inside the face. So what we do is, yes, we can do it. Now, pedestrians and vehicles in the same project, yes, you can do it. Now, this is a very good example. So we detect faces and eyes in the same video, I mean, the same frame. So using the same method, you can detect vehicles and pedestrians if you have the cascade classifiers, the appropriate cascade classifiers, right? So this is uh, a very similar example. So we have the face and the eyes classifier. So now we extract the face, right? So we crop from the rows and columns and y to y plus w, x to x plus w, and we extract the face. And that face, what we are going to do, that face will be applied to the eyes classifier, right? That face will be applied to the eyes classifier, and we get the eyes, right? We get the eyes. And similarly, we iterate through eyes and we draw the eyes. Now, the important thing, since eyes are inside face, we get the cropped image and we pass it to the eyes classifier. But if you are doing it for a multiple objects, then you can do it like this as well. No worries. I mean, differently. You can do it as a different thing. No, we cover the face detection, I mean, vehicle detection as well, right? So what we'll do is, we get the face cropped and that face will be applied to the eyes classifier, and we get the eyes, and we similarly go through the eyes and get it detected. Similarly, detect it and draw rectangles and show like eyes, right? Got it? So this is what you are going to see now. So both eyes and face and eyes are detected, right? So one important thing that we know that eyes will be definitely, they are inside the face, right? Definitely inside the face. So that's why we apply this face into the give me a second. Okay, right. So yeah, so now yeah, so what we are going to do is we detect the face, and face is cropped, right? Face is cropped, and then we apply the cropped face into eyes where we can detect eyes, right? So similar thing is done. We iterate through each eyes in the face, two eyes. So this loop will run twice, and we detect eyes and we plot it here, right? Understood? So that's simply how you are going to perform object detection. Now the next task is to perform this one, something like this. Right? So the purpose is to implement this kind of a thing. right? Okay, so let's see how we are going to do it. So similarly, I think the full that was the full tutorial. Yeah, is that? Oh, this one, right? So what we are going to do here simply, right? We are going to capture bikes in a video file, or you can do it for a camera as well, right? So you know this can be done for the camera as well, right? So what we'll do is simply we get the we have the image source, right? We have the Cascade classifier loaded in Cascade vehicle and pedestrian detection two-wheeler XML. So this is the Cascade classifier, right? And we have the camera source or the video source. So we use this bikes.mp4, but I'm using a available video, but you can do this for your camera as well, right? Then I read a frame from each camera and I blur this image a bit using the cv2.blur function. So we blur the image. Now the image blur is applied since not necessary, but this gives you good results sometimes, not all the times, but sometimes this removes these small noises in the image. So the blurring can be used to remove noises in a given image. So we convert it to a gray. One most important thing when since the cascade classifiers are detected, cascade classifier detects images from gray images, right? So you have to convert it to gray. Then you apply this gray image into the multi-scale, the uh, detection thing. So we apply the gray image and we get the bikes. So what do you mean by bikes? Like similar to faces, right? So number of rows are equals to the number of bikes detected and columns will be XYWH. Remember the same thing, right? Similar to the face detection thing. So then we go through each and every bikes detected and we like this is how we are going to simply implement that. I mean, uh, detect only bike. So we will implement this part and see what happens here. Right? So you can see that it detects only bikes. Similar to faces, right? Similar to faces. This is how you do it. Same thing as the faces, right? Now you may be wondering, okay, at the same time, how to detect faces here? Not practical, but no faces can be detected here. Bike detection file is not there in the drive. Let me have a look. Give me a second. Here it's there, right? It's available as HTML file, right? It's available as HTML file, but you can copy the codes and paste it in IPython notebook, right? So it's available as HTML file. You can get the codes copied and paste it in a Jupyter notebook. Anyway, right? So now if you want to detect some other vehicles in the same video, right? Just repeat these things, right? Just repeat these things, right? A face classifier and do the same thing, the detection in the same image, right? Detect two objects in the same image, right? Got it? uh, Thereafter, what we do now, okay, this is perfect now. You can see that it works fine, right? It works quite fine. It not detecting all the things, but almost all the bikes are detected, right? Almost all the bikes are detected. So what we can do simply is that we can then for this one, I will add some parameters, right? So the idea is here to do something like this. We are going to have a line, right? And if a bike passes this line, we are going to increase the count by 1. So that's what we are going to do, right? That's what we are going to do. So first we will draw a line. Shall we draw a line, right? So what we can do is, yeah, this command can be used to draw a line. So in order to draw a line, it's quite easy to draw a line. Uh, what you have to provide here is simply, if you have the image, if you want to draw a line like this, you have to provide this x1, y1 of this point, and x2, y2 of this point, right? x1, x2, and y1, y2. So these points should be provided, right? So what I'll do here is that I draw a 0 to height minus 200, width into height minus 200. Now, if you are not understanding this, I will explain what this means, right? So the height is, we have to take the height and width first, right? Height and width. So I take the height and the width of the image, right? So image shape, can you remember what image shape gives? Huh? What image shapes gives us? Number of columns, sorry, number of rows, number of columns, and 3 means that we have RGB components. So what that, this is what the image gives. So the number of columns, number of rows, this means the resolution and whether it's a color image or not. So if we have color image, we have 3 here. So this is the height and this is the width. So we take the first 2 elements of the image shape. So that means height is taken here, width is taken here. This is taken here, and this is taken here. So we have the height and the width of the image. Using the height image dot shape, we can take the height and the width, right? Thereafter, what you do, this is how you draw a line, right? So height minus 200. So that's the y parameter, and x is 0, right? So this point, if you take this point, so this is the height. That means 1 something, right? What was the height? 720, sorry. So 720. So we take 720 minus 200. That means this point, and you know the x is 0. And this point, this is the same y, right? Height minus 200, but x will be the width. X will be 1200 something, right? So x is this one and the y is the same. Y is the same, right? So we draw a line using that idea here, right? So this is how we are going to draw a line. So if you run this one now, you will see something like this. Okay, so a kind of a yellow line is drawn from 0 height minus 2 and width height minus 20 to 200, height minus 200, sorry, height minus 200. Got it? So we have drawn a line here. Then what we'll do, we simply then we have to do what? Yeah. So then what we'll do, uh, we take the center of the bike as well as the center of the line, right? So you know the bike, when a bike is detected, let me show you. When a bike is detected, you have X, Y, right? So you have X and Y and W and H, right? So how we are going to get the center of the bike? I mean, the x coordinate is not important here, right? So we are not worried about whether the bike is here or the bike is here or bike is here. The x parameter is not going to be a matter, right? But we want to check whether the y parameter, if the y parameter pass this line, okay, then the bike, we can conclude that the bike is past this line, right? Bike passing this line, but no need to, like, no matter where the bike is, right? The x coordinate is not going to be a matter. So we will get the y coordinate of the bike, right? So the y coordinate of the bike by center, let's say we get the center. So you can see it will be y, what? Y plus h divided by 2, right? Yes, y plus h divided by 2. That marks the center, the y coordinate of the center y coordinate of the bike, right? This is y, you know, this is y, and h divided by 2. So it marks the center y coordinate of the bike. Now, the important thing, that x is not going to be a matter, where the bike is not going to be a matter. All right, got it? So we are not worrying about the x coordinate. So what I have done here, I got the y plus h divided by 2. Since it can be a float number, I convert it to int and I take the center line. But you know the center line, the y coordinate of the line is height minus 200. That's something obvious, right? So we have defined the line in the y direction, height minus 200, the whole length minus 200. So this is the line, right? So what we have to do, we have to check whether this line passes this yellow line. We have to check whether this line passes the yellow line, right? So what we'll do here, we'll simply do something like this. So I define something like this. I'll first do it like this. Okay, this is what you are going to do it, right? Okay, if line cy, the y coordinate of the line equals to the y coordinate of the center of the bike, y coordinates of the center of the bike, right? Then I increase a value called count by 1. So let me define the count equals to 0, and I define the count by 1. So then let me print the count here, right? So now we will see. So this is what the idea that we get at the first time, right? So if the center point of the bike pass the uh, line y value, then the count should be increased by 1. So we'll run this and see whether it's going to work or not. No, the count is not increasing. Can you see? Now the bike passes the line, but the count not increasing, right? Any idea why? The count is not increasing. You can't see, right? Anyway, let me get it here. So that you can see the count is not printed. The count is not increasing. Count is 0. Now 1 detected. Now we have like 20 bikes past this line, but only 1 detected. Can you identify the reason? What's the reason for this? Can you guess what's the reason? Now, in this case, what happens? We are checking whether the line and the scent of the bike is the same, right? It's the same, but always it won't. And now, can you see now this is blinking kind of thing? That means sometimes it's not detected, right? Sometimes it's not detected, and you can, I mean, these are fundamentals of programming. Now, this loop runs, right? This loop runs iteratively, and sometimes when we check, I mean, this loop done several things inside this while loop, right? It detects this, it draws this and everything. So this takes some time, right? I mean, in order to convert color, in order to get the shape, in order to detect the bikes, in order to draw this line. So everything takes some time, right? But when at the moment you check this condition, sometimes it's not equal, right? So it means that the same, I mean, so it's like a very rare occasion, right? At the same time you check this condition, at the same time the two y coordinates should be the same, but the bike is moving. Sometimes when the y coordinates are same in the line and the bike somewhere here, when 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 drawing this line, yes, in that case these two might be the same, right? I mean, this is not the programming, they don't, I mean, it doesn't do these things parallelly, right? So it's a sequential thing. Sometimes when, I mean, when this is checked, when it check this condition, sometimes the bike is past the line or before the line, right? So it's quite rare to uh, yeah. So therefore what I'm doing is not checks the whole value, I mean the same, I mean the value exactly equal to the y coordinates. No, I'm not checking that, but I'm giving some kind of a threshold, right? And I'm doing something like this, right? I'm checking whether the, like, the line is in this kind of a range, not the same, but in a range like +6 or -6. So that means for this kind of example, like +6 -6 range, right? So if it is, the bike is detected in that range, okay, then the count will be increased by 1. So now what happens if you run this one, probably you will see that the count is increasing, probably. Yes, 1, 2, 3, 4, 5, 6, 7, right? So now it's not perfect, but works well than the other case, right? So now you can see the count is simply increasing, right? Understood? So done. So that's all. Then we have like do some uh, things like this. So I'm taking this kind of a region, right? And I make it 0 to 7, 0 to width, and I make it R, red color. So see what happens. So here, can you see? So 0 to 70 in the height and O throughout the width. So I'm going to make that area equals to R, right? I make that area equals to R. So I make a red color rectangle. Now this is where we show the count and everything, right? So then what I'll do, that's all. And yeah, then I can put the byte count like this. I'll put the byte count, yeah, here. Right. So what I have done here is I simply show the byte count, and I provide the count converted to a string, and this 150 where the count is shown. So that means this is the position of the text, right? Position of the text and the font scale, I hope you can remember, and the font color is white and the font thickness is 2. We explain these things, right? So you can see. 50 10. So 50 10. So this is where the text is placed. 50 y50 x10. Right? Understood? Y50 x10. The x and y values are given here. See, 150. Sorry, 150. We have changed it a bit. 150. Right. So then that's all. Now, but the thing is, now you can see some kind of a detection here, right? See only the yellow color, like detecting that no any interactive feedback provided, right? So therefore, what I'll do is I change the line of the color of this line. So if it's in yellow, I change that color when a bike is detected. So how we are going to do that? When a bike is detected, I make the color of this same line to red. Right? So you can see now when in the inside this if condition we are doing it, right? Inside this if condition you are doing it. When a line is detected, you can see when a line is detected, we change the line. So the line was in yellow color, but we change it to red color now. So when a line is detected, the line becomes red. Only the color is changed. All the other parameters are there. The yellow color line becomes red when a bike is detected in this line. See, right? Okay. So yeah, so that's it. So very simply, we implemented the bike counter. Now the thing here, the object detection is something now like this. So the face detection code, you will find it anywhere in the internet. So that's a very common thing, right? So something implemented in 2002, the face detection. So you will find it anywhere in the internet. So if you search for face detection, yes, the code and the file, all the things will be there. But the thing is that you have to always think of a method of using it for this kind of application, your own application, right? Now, just copying and pasting the code and detecting faces not going to do anything. But here is a very good example. We can detect bikes. That code will be there in the internet, bike detection. But doing it your, converting it to your, modifying it to your own application is something new, right? In order to do that, you need then you can see that you need to think a bit, think out of the box. And in order to do that, this is the idea simply. Okay, this is the idea simply. This is what I build. I create a line, and if the line pass, the bike is past the line, then I increase the count. So this is something that, okay, it's common. I'm not saying that this is a genius idea, but it's some kind of a good idea. But the thing is, in order to implement it in a code, you need the coding skill, right? So that's what you want to get actually, right? So in order, the only method of getting it by doing it. Don't think running a code in the internet or just reading a book or following a tutorial. No, it's not going to do anything to you. No any change. You will get the knowledge and you will get it like, yeah. But the most effective way is getting the programming skill, the coding skill is by doing it. So you have to run the codes and you have to play with the codes and you can change. Now you can change this 6 value and see what happens, right? Understood? So these are tunable parameters. And see now, sometimes if you change this value to like some other value, the the detection will be more accurate, right? Likewise, you have to always change these things and see. That's why I say like I to ask you to play with these codes, and that's the only method you are getting this knowledge, right? Buddy, right? So uh, I have given you all the codes. Now you have lots of works to do, right? So you can similarly. Other thing is apply this into different applications. Now we have done it for bike detection. So I have given you lots of cascade classifiers, right? In vehicle and right, cars, bus, front, two-wheeler, pedestrian. So what you can do? Implement this for a pedestrian count, implement this for a car count, and see what you are going to get, right? So you have lots of things to be done after this workshop, right? And also, can you remember the face detection thing? So do it for your own family members and get the results, right? So we have lots of things to be done after this workshop. So that's something that's something with you. The responsibility is with you, right? So I hope you will work with these things and try to implement your own project. So that's the most important thing at the end. So you should be able to implement it for your own application. That should be the final target. Otherwise, doing what I'm doing, or otherwise doing something in the internet, doing something available in the YouTube is not going to help you, right? So what you have to do is apply this to your application and try to do your own work, right? Okay. So I wish you all the best for the your future, and try to implement this and try to do these things in your projects and coming works. So I always encourage you to do those things, right? So anything, since you asked, if you want to contact me for any kind of issue or any doubt you may have, you can uh, contact me through this email, right? uh, no, you are going to have lifetime access. So I think the videos that you have provided, you can access it anytime, anywhere you want. And the next thing that we are going to have another advanced workshop for deep learning neural networks. So in that one, you will get a very good idea about neural networks and deep learning, a very good thing, a very advanced workshop, right? The deep learning workshop probably will be in January. So you will get to know about this soon, right? So it will be in January, for second week of the January most probably. So we will inform you soon, right? So that will like the most trending and the newest thing, the novel things will be discussed about their neural networks, right? So you will get to know about those things in future. You will get to know about those things. Okay, so thank you very much. And if you have any doubts, you can ask them now before concluding the workshop.
Sir, I have a question.
Yes.
So, is it possible to implement these machine learning codes in a, let's say, a mobile app or a web app?
Yes, exactly. Now, uh, Aryan, right? So we actually what we did as the example for the linear regression was a very good example for that, right? I think you got that thing, right? The video. Uh, yeah. So in that we implement. Now it's very possible, right? So we can implement this like Python backend. We can create a Python backend, and thereafter we can implement it in a web application or a mobile application. So let me show you an example that we did on the day 4 probably, right? Uh, so I think you got the video of this one. Yeah, yeah. So this half risk level predicting thing, right? Right. So this kind of web application you can simply create, right? So now this uses the linear regression algorithm. Can you remember that I provided you in the we did this on the last time, right? The heart risk level prediction using linear regression. So it gives you the result, right? Risk level. So this kind of I mean, this is a very fundamental application, but this is the method. So you can use Flask, Django, anything, and create a Python backend and integrate these saved models. So you know how the models are saved, right? And then these can be deployed into a server, a paid server, and you can get this thing. So let me show you a thing. Now I have deployed this similar application in a web application. No, not this one, but you can do it. So the Flask and Django you can use, and I hope that you got the video of the implementation of this hard risk level application, right? So then by going through that, you will get the fundamental knowledge on how to create backends in Python, and then it's a matter of creating the front end. After creating the Python backend, you get knowledge on how to create the Python backend in the video that you got yesterday. And with that, it's a matter of creating the front end. So if you can create the front end, it can be like Python backend will be the same. So the same Python backend, the front end you can create it to a web application, or you can use React Native or whatever the front end development for mobile application, and you can develop it as a mobile application. So that's simply after creating the Python backend, it's a matter of creating the front end in web application for a mobile application, right? Okay, so yeah, so Django and Flask, we are planning to arrange a workshop for Django and Flask in the future. You will get to know about these future coming. Yeah, uh, yeah. So this is a very good uh, experience for you. Yeah, so this will definitely provide you more experience, and you can provide. I think you are getting a certificate, so you can present that as well. And if you are dealing with like self-driving cars, probably the idea, what will most important will be the deep learning workshop, deep learning and neural network workshop. You are going to get more idea about convolutional neural networks, recurrent neural networks, and everything. So that's where you are going to get the idea about neural networks and self-driving cars. So that would be the ideal phase, right? Okay. So any other question from you all? And if you have any other doubt, you can always contact me through my email as well. So any other from your side? Okay, then. So thank you very much. Hope you got a good understanding about machine learning and also the real project implementation. So I wish you all the best for future endeavors, and I hope to see you on future coming workshops for machine learning, sorry, deep learning and other advanced workshops. So thank you very much, and we will meet again with the advanced workshop.